Swayam Prabha. Digital India. Educated India.
Welcome back. Today we are going to start our lecture number 30. We are discussing the fluorescence anisotropy and we are done till the Perrin equation. So, what is Perrin equation? Let me write it once again. So, Perrin equation is written as R 0 by R S S equal to 1 plus tau f divided by tau O R. So, where this R 0 value is initial anisotropy, R S S my steady state anisotropy, and this tau f is my fluorescence lifetime, and tau r is orientational relaxation time. So, from here what you can see is that without, if you have some idea about this value of R 0, right, and this R S S can be measured very easily from this fluorimeter, where you have this polarizer and analyzer. Right. Normal fluorimeter does not have this polarizer analyzer, but if you can install a polarizer analyzer, so that your excitation light is polarized light and the emission you are going to analyze which is the perpendicular direction and which is what is the intensity of the perpendicular direction and what is the intensity of the parallel direction, then you will be able to calculate this R steady state easily. Right. And if you have this knowledge of this fluorescence lifetime, then you will be able to calculate this tau R. Now, if you recall that our Stokes-Einstein relationship, then this tau r can be written as tau r equal to eta v by R t. Right? This is my Stokes-Einstein relationship, where this eta is equal to the viscosity of the medium V is molecular volume and R is my universal gas constant and T is my absolute temperature. Now, if I plug in this expression for this tau r in the Perrin equation, what we will going to see is the following: 1 over R S S equal to 1 over R 0 plus tau f into R divided by R 0 into V into temperature by viscosity. Right. It means that now, if I plot, this is the measurable quantity, this is your measurable quantity, this is the property at a particular temperature, obviously you know the viscosity. So, then T by eta is a known quantity, and I can measure this R steady state for a different value of T by eta. I change the temperature, obviously viscosity will change, so T by eta will change, and for a different values of this T by eta I can measure this steady state anisotropy, and then I can plot it. Right. So, let us plot that same. So, if I plot, what we are going to see is 1 over R steady state versus T by eta. You are going to see a straight line and intercept will be equal to 1 over R 0. So, from here you will get some idea of this R 0, right? And then slope will be equal to tau f R by R 0 V. Now, if tau f, the fluorescence lifetime is known, R obviously is a constant, and R 0, if you have a prior idea of this R 0, then you can calculate V, that is the volume, and this is a well used equation in application of the fluorescence anisotropy. So, from with this you can actually determine the size of, let's say you are working with a protein and this protein is getting denatured. Once the protein is getting denatured, the size will increase, and if you have one fluorophore already attached to the protein, then by measuring the fluorescence anisotropy, that means the fluorescence this RSS value, by measuring this RSS value, what you will be able to do, you will be able to see that at this particular condition what is the volume of the protein, that means the size of the protein and so on. Right. Now, one of the important thing here is that what will be the value of R 0, right? That is the biggest question, right. So, that should be measured, otherwise I cannot say anything about this. And we have seen that limiting value of R 0, you remember our first equation, I have written R equal to I parallel minus I perpendicular divided by I parallel plus twice I perpendicular. Right now, I am not talking of, I am not including this G, because considering that G equal to 1, if G is there, then just a factor will be there, right. So, consider that G value is equal to 1, and I am now doing all those things. Now, in case of time dependence, then this is nothing but R t is equal to I parallel t minus I perpendicular t and so on. So, that means at time t equal to 0, that is my initial anisotropy R 0, and that is whatever I have written here as R 0. So, in this case I have to determine what will be the value from that particular equation. When I said that it is I parallel minus I perpendicular divided by I parallel plus twice I perpendicular, obviously at time t equal to 0 there was no emission from this perpendicular component, and there is only emission from this parallel component, makes it R 0 equal to 1. But whether this is true, and I also said that when this R value will change as time goes, because the intensity of the perpendicular component will increase and parallel component will decrease because of the reorientations of the molecules or transition dipoles when at the excited state. So, as time goes, there will be the intensity of the parallel and perpendicular components will be equal, and in that case you will see that R will going to be 0 ultimately at after a certain time. Now, let us see these things, right, in more detailed way. So, let us now consider that you have excited the molecules along z axis. So, z axis is your polarization for the excitation light. Okay. So, let me write here. So, polarization of the excitation light is along z. I consider it over here. So, if I consider that only those molecules, that is why I said that only the molecule whose transition moments are along the z axis, they will be preferentially excited. That is what I said earlier. Again I am telling the same thing. So, those molecules will be excited, and if the direction of the absorption transition moment and emission transition moments are same, like they are collinear, then the emission will be also along z axis. That is my condition now I am imposing. Here the direction of the absorption transition moment and emission transition moment, they are collinear, then the emission will be also along the z axis. Take a note on that. Okay. Now, let me tell you that now the molecule has been rotated at an angle theta, right, and now I am looking at this molecule. So, now this bold arrow is my molecule which has been rotated at an angle theta from the direction of the excitation, and now I am looking at this molecule. So, here you see the rotation of the molecule makes a component of this I parallel as cosine theta, as you know, and but the molecule can rotate, like if this is my z axis, the molecule can rotate from here to this side as well as from here to this side. In all the cases the angle is theta, this side angle is theta, this side angle is theta. That means I need to worry about all these different angles for a fixed value of theta. That means if I assign this angle as phi, then the value of phi should be 0 to 2 pi. That is what I have written over here. So, now here you see for this perpendicular component, this should be sin theta sin phi, correct. So, the intensity, those are the electric field. So, intensity I parallel will be equal to cos square theta and I perpendicular will be sin square theta sin square phi. But here also please note that we should take all values of sin square phi. That means, I should take the sin square phi average, right. So, I should take the sin square phi average. So, let me find out that. So, sin square phi average is equal to integration 0 to 2 pi sin square phi d phi divided by integration 0 to 2 pi d phi. So, and I already got this I parallel equal to like this, I perpendicular is